Hi, today we present Dynamic Reap and how to bring life into simulations for UAV planning and acting frameworks. Real-world test cases of AI planning methods for UAVs involve several risks.
Whoa!
That is why we use simulators for debugging and prototyping. Most simulators focus either on low-level physics or are highly abstracted. REAP, presented on ICAPS 2023, tries to bridge this gap. Nevertheless, the approach has two major drawbacks. First, it assumes a static world, which means there are no changes during mission execution in the simulation world. This is not a realistic assumption for real missions. Second, it is based on LiDAR scans, which means it offers no semantic segmentation of the world. That makes it hard to validate symbolic planning and acting methods. Dynamic Reap addresses these two drawbacks. Let's have a quick look at our system diagram. On the right-hand side, you can see the simulation part. At its core, there is Unreal Engine 5.2 with the AirSim Colosseum plugin. We will take a closer look at the features in a moment. The simulated UAV is controlled by a simulated PX4 flight controller. On the left-hand side is the planning and execution framework. For this demonstration, we use the Auspex framework. It offers a planning module that includes the unified planning library. An execution module is monitoring and executing the actions by sending commands to the PX4 flight controller. We have to mention that this is the same interface as for real hardware flight controllers. A knowledge base module stores real-world map data and mission data, which includes the planning problem. Finally, a sensing module receives a camera stream for visual perception. Now we will take a closer look at the features of our simulation environment. The first feature is that our levels are based on georeferenced height maps. We can use open source tools, for example this Unreal Height Mapper, to select an area and get the height map from free available map data. It generates a grayscale PNG image for us, which can be then imported to Unreal. It also computes the correct scaling for using a GPS coordinate system in Unreal Engine. We now select the file, import it to Unreal to generate a landscape. This is the basis for our level. On the right hand side, you can see the same section of Google Earth. Afterwards, we can add textures, objects, buildings, landscape features, and vegetation like trees to get a realistic environment. Georeferencing can be achieved by using a georeference plugin for Unreal Engine. For that, we set a reference point at the edge of the map or a prominent geographic point like a summit and enter the GPS coordinates. Then all objects in the map can use this WGS84 coordinate system to get its current GPS position. In this example, it's printed on the left side. Next feature is the integration of AirSim as plugin for Unreal Engine. We use Colosseum, which is a AirSim fork that supports Unreal 5 or higher. AirSim simulates flight dynamics inside Unreal Engine of a UAV and is controlled by a simulated PX4 flight controller, which offers an interface for the Auspex framework. It also can simulate a camera inside the simulation environment, seen at the right side, and the camera stream is published as ROS2 message. Next feature is the integration of AI-controlled NPCs. Unreal Engine offers the possibility to add a navigation mesh for AI-controlled NPCs and computes collision-free path inside the mesh, which can be made visual as a green overlay in the map editor. We now can add waypoints for the NPCs to the map. And when we start the simulation, the NPC begins to walk his list of waypoints. We also can add randomized events so that the NPC stops following his path and moves to one or more random position. For example, here he stops walking his path and gets lost in the forest. Another feature is a third-person player mode. We implemented a logic to take control over an NPC. Then the NPC can be controlled via keyboard in a game-like manner. This works also concurrently with AirSim simulation, so we control the player while the UAV is flying. Finally, we present a complete run of the example search mission. For the planning and execution part, we deployed the Auspex framework as mentioned earlier. It connects to the simulated flight controller via micro XRC agent for off-board control of the simulated UAV. It is configured to use an integrated PDDL planner for plan generation. As soon as the simulation starts, the NPC hiker follows the predefined waypoints. However, it is not predefined how the scenario ends. In this case, the planner receives a search mission problem with the information that the last known position of the hiker was at a summit called Hahnenkopf and is now lost at the way back. Based on that, the planner generates actions which can be seen on the left side. It includes searching a computed area, and as the map is georeferenced, the planned waypoints of the UAV can be plotted on a map, seen on the right side. The name of the summit can be resolved to an actual GPS position. First action of the UAV is takeoff, and when the desired height is reached, it moves to the last known position. After that, it searches the area with a search flight pattern. As the camera's image is streamed to the connected system, an object detection can be performed and is able to detect a person. The detection is stored in the knowledge base, and if defined as an optional goal, it leads to mission success. In this case, the UAV returns to its home position and lands. As the outcome of the scenario is not predefined, also other variants are possible. We show a second example where the hiker did not reach the summit and is lost in a forest area. Based on this different information, the planner generates different actions which are then executed in the environment. We hope it was interesting and thanks for your attention.